we're looking at binary trees specifically this week. So let's talk about them. So basically, binary trees are very, very similar to what we talked about with linked lists. The only difference here is that they're not linear. So it's not start here and, you know, I have one trail through here. So it's not just like a line, right? So we call those nonlinear. And basically each of these are going to have a node, all right? And they can point to 0 nodes, 1 node, or 2 nodes. Okay, so before when we saw a linked list and it was kind of this chain scenario, here we have you know, where we can go to 2 different directions, you can see. So we can split off at this, you can see this top one into a left and a right node, for example, and that can be split off into a left. And you can see some of these have no nodes connected to them. So this guy here at the bottom, I think you can see my cursor, is not connected to any. This one up here is obviously connected to this one right below it. And we have some definitions, so we'll get there in a second. But basically we have data values, right? Just like we did before. But we also have then these pointers to point to these other nodes to which we're connected, all right? So what we have with a binary tree is we have a tree pointer, which basically points to the tree. So just like a head pointer in a linked list, it points to our first node in the binary tree. And we have a root node at the top of the tree. So that's the actual top of the tree here. So this is an actual node, all right? This tree pointer is not a node in itself, but it's pointing to the first node, all right, or our root node. So we mentioned that some of these won't have any, well, let's introduce the terminology of parents and children, right? So basically, the number 19 here is a parent to number 7, which is its child, right? Because 19 is pointing down, you see to 7, okay? Now you see number 7 here, the node that has the value 7 in it, doesn't have any children, okay? So we call that a leaf node. We're talking about trees, right? So we got to talk about leaves. So there are basically no branches here. It's just a leaf, okay? You can see both of these point to null, right? So these next pointers point to null. So this becomes a leaf then. And you can see in this tree where we have these 5 nodes, 7, 19, 31, 59, 43. You see 7 and 43 are both leaf nodes because they don't have any children, okay? Notice that 31 is the root node, and 31 has children of 19 and 59, right? And then 19's child is 7, and 59's child is 43. Okay, so yes, those nodes that are below a particular node, we call those child nodes or children. Okay, so I just mentioned that the children of the node containing 31 are 19 and 59. All right. Parent nodes are going the opposite direction, right? So the parent node of 43 here is 59, and the parent of 59 is 31. And yes, you can say that the, I guess I've heard this terminology before, and you don't hear it too often, but 31 would be the grandparent of 43, right? So we can split up a tree into its parts, and we can have subtrees, okay, that basically are just a part of the tree, all right? So 19 and 7, we call these in the left subtree of 31, okay, because yeah, they're coming in from the left side here, right? So, and yes, you'll see that these are in a particular order for a reason. We'll talk about that more in a bit here. So 7, 19, constitute the left subtree, and then we'd say that 59 and 43 are 31's right subtree. Okay. So we can use this binary tree to help us organize elements, data, and search those data. Okay. And the idea is if we organize these values in a certain way, then we can get some really efficient searching going on here. All right. Notice the left subtree of a node has values that are less than the node. So notice in the left subtree of 31, we have the values 19 and 7, which are both less than 31. All right. And the right subtree, we have values that are greater, right? So we have 59 and 43 in the right subtree, which are obviously both greater than 31. So with those assumptions, we can then see that searching in a binary tree would constitute these steps. Okay, so we always start at the root node, and then we look at the data in that root node, and we check, is this the value? So go back to binary search and remember that we find that middle value, right? And then we look at that value and we compare it to the value that we're looking for. Same thing here. We start at the root node and do that exact same thing. Is this the value that we're looking for? If it's not, then we're going to compare. Is it less than, is the data that we're looking for less than the value in that node? And if it is, we're then going to then go look in the left subtree. All right. And you can start to see how this lends itself very well to recursion, right? Because then we can keep checking the new value and checking is it greater than or less than, and then searching left and right. Because realize, you know, we can go a lot of different levels down on these trees. Okay. But if it's not less than, then we assume if it's not equal, if it's not less than, then it has to be greater than, right? So then we would look at the right subtree. Okay. And then we continue doing that. We repeat those steps until we find the value or we reach a null pointer. All right. Now, if we reach a null pointer, that means we haven't found the value in our tree. It doesn't exist in our tree. So let's look at an example. So with this tree here, we have, we're looking for the value 43. All right. So we start at the root node. So we look at that and we compare the value 43 to what's there, right? Well, there's a 31 there. Well, that's not the value we're looking for. So then we ask, is it less than, right? No, it's not less than. It is greater than, right? So that means we're going to look at the right subtree. So then we're going to look at now, we're going to change the node that we're looking at to 31's right subtree, so subchild, if you will, the child on the right side, the right child. So then we're going to go to the right child, which is 59. Okay. Then we ask, is 59 the number we're looking for, 43? No, it's not equal. Okay. Is it less than? Yes. The number we're looking for, 43, is less than the value that's here. That's 59. So then we're going to look at the left. So now we look at the left child. Well, the left child, we go look and it's 43. Is 43 equal to the value we're looking for? Yes, it is 43, right? 43 double equals 43. So we're good. We found it. Okay. Any questions on this procedure? Pretty straightforward, right? And yet so simplistic. Isn't it great? Right, so let's see some operations we have available to us. With binary search trees, we're going to need to create a tree, right? Which means organizing the data properly into a binary search tree. And I realize that with a binary search tree, we do need to follow this scenario where the left is less than the parent and the right is greater than, okay? So creating a binary search tree or organizing the data into a properly formed binary search tree is the first thing that we're going to want to do. Inserting a node into a tree, into an already existing tree, that's the next thing, which is putting the node where it belongs, right, into its proper place. Okay, and then finding a node that we just kind of talked about is locating a node with a particular data value. And then finally deleting a node from a tree, right? So removing the node and adjusting the links so that we maintain the structure of the tree. Okay? Those are the things we'll be looking at doing this week. So think of a node in a binary tree just like the node with a linked list. So this should look kind of familiar, except the only difference is we have two node pointer fields here. Yeah, we have a left and a right pointer, okay? So there's the value itself, which in this case is an integer in this struct, all right? And then we have left and right nodes, which point to the left and right children. So to start, to create a new node, we need to allocate memory for that new node. So we would do that with this kind of command, right? New node equals new tree node. Okay, then we need to initialize the contents of the node. So set the value equal to some number, right? That comes in, whatever value it is that we want to set it to. And then we need to set the left and right pointers. So notice this command here would set our left and right pointer equal to null pointers. Okay. So here in this example, we are assigning 23 to the value. Okay, and then we're assigning the left and right pointers to null.